Okay, so we can look at the table, and you spotted it. There are actually two things on the table that involve, that match this. One is a transform of a Heaviside function, okay? And you don't know what a Heaviside function is. I just told you, it's 0 all the way up to x equals 0, and after that it's 1 forever, okay? And you could easily integrate that. But we don't need that one. The one we want to see is, well, the table says, and they use alpha?
Yeah.
One over s minus alpha. Now that one's really easy. If you plug in e to the alpha t instead of f of t, the integral is totally straightforward. So you can verify that in about 12 seconds flat. Well, somewhere between that and 12 minutes, and if it takes you 12 minutes, you need to practice your integration. But, okay, I mean, you're just integrating e to the negative quantity t plus alpha times s, okay? You got to get a 1 over t plus alpha. You're going to substitute stuff in here, and you're going to get this very quickly, about 3 steps. No integration by parts, no tricks, just very straightforward, okay? Okay, so anyhow, that's what the table says. This is probably the second easiest integral on the whole table. The easiest one is where f of t is 1, okay? So, and as I say, most of them are easy. Anyhow, you have this, okay? So, one over s plus 5 equals 1 over s minus alpha if what?
Alpha's -5.
Yeah. So, one over s plus 5, Laplace transform of e to the negative 5t. Okay? And negative 4 times s plus 5 is a Laplace transform of negative 4 e to the negative 5t. Because, of course, if you integrate this, you get negative 4 times whatever you get when you integrate this, right? Which has to be this if you integrate this and get this, right? You know, integrate it with the e to the negative. I pointed wrong, but it's clear. Should be clear from the linearity. If you integrate this with an e to the negative st from 0 to infinity, you're going to get negative 4 times whatever you get when you integrate this. I said it right the first time. I pointed right. I just forget where I'm pointing. I'm not even looking at what I point at. Let me say it right. If you integrate this with e to the negative st from 0 to infinity, you get negative 4 times what you get when you integrate this. Okay? So it follows that since when you integrate this, you get this. When you integrate this, you have to get this. Which is, of course, what we're trying to figure out. What do you have to integrate to get this? That's the inverse transform. So we put this in terms of an inverse transform of negative 4 over s plus 5. We say that's negative 4 e to the negative 5t. And that is solution to this with this initial condition. I mean, that's the first type of, first order linear homogeneous with a very simple function in front of y. And just by inspection, you know that e to the negative 5t or any multiple of it has to do this, because the derivative is going to be negative 5 e to the negative 5t, and this is going to be 5 e to the negative 5t. They add up to 0. And that should be something you're totally tuned in on. Okay? Because a lot of stuff we do just follows from that. From that kind of reasoning. Okay. So we just solved this problem using Laplace transforms. Now you say, why would we want to do this? Well, for this function we wouldn't, because the solution is so trivial. Okay? But if I have some bizarre function here that I know how to integrate, or if out of the functions that we have in a more complicated equation, because we can't integrate this function, we can't solve this one. Okay? Or if we have something over here that we don't know how to integrate, but we do know how to, if we use our integrating factor, we won't be able to integrate this thing, okay? But a lot of times, by Laplace transforming it into an algebraic equation, we can still get a solution. Because this function, before you multiply it by the integrating factor, might be perfectly integrable, okay? But it doesn't match up with the function you got in front of y in such a way that you can do that integral. You can Laplace transform it and get it. Now there's another advantage to the Laplace transform. Let's say you've got a damped pendulum, which we looked at last time, simple second order equation with constant coefficients. If you assume a drag force that's proportional to velocity, you get a very simple equation that you can solve. You get a characteristic equation, you solve it, it's a quadratic equation, you plug back in, you get your solution. Then adapt it to whatever initial conditions or boundary conditions, okay? That's straightforward. What's not straightforward is what happens with that equation if we take a baseball bat and hit the thing. You have an impulsive force, okay? You can't deal with an impulsive force. Now you might go to physics and say, okay, well that changes the velocity, which changes everything. Now we've got another equation with different conditions that match the conditions we had plus whatever momentum we imparted to the system. You can do that. In the analogous electrical circuit, which has an identical type of equation using capacitors and inductors, and in physics yesterday we talked about inductance a little bit, okay? The voltage that you induce as a flux through a surface changes, okay? And we didn't do much with that, so I don't expect you to be tuned in on it, but you know, we take that to a device like a coil that has some kind of inductance. You end up with a second order equation with constant coefficients, okay? So what happens if lightning strikes it? Just a little bit of lightning. You have an impulsive,
I guess it'll get fried.
analogous to an impulsive force, okay? Now if you have a circuit of that nature, it can oscillate just like a pendulum can. Total analogy, okay? What happens from that impulsive voltage, okay? Laplace transforms allow us to deal with that. Also, with circuits, or even with pendulums. Okay, let's say we've got a pendulum, but we're driving it with some force. Okay, well, your equation is going to look something like y double prime plus gamma over m y prime plus k over m y equals some function f of t, right? Well, this is going to transform into a quadratic function of y, just like this transformed into a linear function. Okay? I've got that off the board yet, but when we transform this, we got the Laplace transform of this plus this, and it all came down to a linear function of the Laplace transform of y, right? Well, we've got a couple of derivatives here, so because of what we do, and I don't want to go into the detail of it, it's very simple, okay? We get a quadratic function of Laplace transform of y. That's it, y. Okay? And that's equal to the Laplace transform of f of t. Okay? So now, if we got something we can do the Laplace transform of up here, we just solve that quadratic. You know, bring that over on this side, and of course it's not necessarily quadratic anymore. So now this is an algebraic equation. We can do the algebra and solve for L of y. We get in the inverse transform it, we get the solution to the equation, as we did over here in this very simple example. Well, if f of t is cosine, okay? Maybe I was thinking asinine or something, I don't know. Cosine function, okay? And we'll say a simple sine or cosine function, like a sine of omega t plus phi, okay? We don't need the Laplace transform. The equation is going to be very simple. It's a cosine. It's going to be s over s squared plus alpha squared, right? Omega squared. Okay? And we multiply that. Well, it's a fourth degree equation now. So maybe we'll have a little trouble solving it, but maybe not. Okay? But we don't need that. All we have to do in that case, and we haven't done it, is say, okay, y is going to be some linear combination of sines and cosines, because that's the only way the derivatives are going to add up to a sine or a cosine. Okay? And that works out very easily. Very easy to solve. Okay? So, an f of t function that looks like this We don't need Laplace transforms. However, let's say that with some frequency that doesn't match the natural frequency of your pendulum, okay, you're alternately exerting a force for 1 second and then letting it go. Exert a force for 1 second, let it go. Exert a force for 1 second, let it go. Okay? And you're not doing that in sync with a pendulum like it'd be, for example, if you're pushing a kid on a swing. Is that still legal?
Haven't done it lately.
It must not be legal then, because you'd have done it if it was. Okay. Yeah, maybe you haven't been around kids, you know. If you don't synchronize your push with the swing, things get weird. It doesn't work very well. Okay? Well, that corresponds to a force function that might look like this. Push, nothing, right? And yeah, you kind of go ahead and connect these things, but the vertical lines don't mean anything. But this is what you call a square wave, right? Only way to solve that, I won't say the only way, there might be some esoteric thing I'm not aware of, okay? There are a lot of things I'm not aware of. But the only way, using standard techniques at this level, and it works very well, is to use Laplace transform, okay? Same goes for a triangular wave where your force increases linearly, then decreases linearly with equal but opposite slopes. Okay? You can Laplace transform this. You can Laplace transform this because they're periodic. Okay? So if you can transform one part of this thing, you can then easily write down the transform for the whole infinite thing. Okay? And showing why that works is no harder than what we've already done. Except you got to work it through. Okay? So there are rules for doing that. There are rules for applying these transforms. The rules are not deep. Okay? I mean, if you go deep enough into the subject, yeah, but we're not going to go that deep. The rules that we're going to use are not deep. They're just based on what you know about mostly second semester and first semester calculus. Okay? No multivariable calculus necessary. And the first year calculus you got to use is not difficult. And it's not trivial, but it's something you expect everybody to be able to do in the final. Okay? Not something you just expect the very top students to be able to do. It's something you expect everybody that passes the course to do. Okay? So nothing to fear, and actually there are a lot of advantages, and you'll see, because of course we're doing physics at the same time we're doing this, and we're going to analyze circuits. Pardon?
That'll be fun.
Yeah, and these techniques are going to come right out of that. Now, we're not going to use these techniques, but you'll understand how they can be used. Okay? In other words, our first year physics students aren't going to know a lot of things that you do, You know, they can understand a square wave, and it's very easy to generate a square wave. You crank the generator, you stop. You crank the generator, you stop. Crank the generator, stop. Or you have a battery, you throw a switch to engage it, throw a switch to disengage it. Throw a switch, take it off. Throw it, open it. Close it, open it, and you get a square wave. And you see, with one of these fancy little vernier interfaces, the solutions you get. Okay? And, well, I'm not going to go into any more detail. So everybody's going to see that. But you'll also know that you can do this. Okay? And in electromagnetism, you'll have a better understanding of Maxwell's equations. We can't even really quite talk about how they're written for somebody that hasn't had multivariable calculus, doesn't know what gradient is and stuff. Because it's all in terms of gradients and surface intervals and integral theorems. Okay? Very powerful. Very, very powerful stuff. Okay? And this lets us grab onto something we can't grab onto any other way. But something that occurs naturally. Throw the switch, take it off. Throw the switch, take it off. Just keep doing that. Okay? What's your function? What's your response function? And what currents? What's your current function is a function of time. Okay? Okay, so that's what Laplace transforms are good for. So I'm going to give you a few problems to get your feet wet with Laplace transforms. So when we get deeper into them at the end of the term, someday after you finally get a textbook,
Whoops.
yeah, you should have ordered that thing 2 weeks ago. And until you get a textbook, we're going to keep piecing around at things that are relevant to what you're learning in physics, and things that are going to give you the foundation for working through all the gory details, which aren't all that gory. This course, with a couple of exceptions, is not all that gory. Nothing we've done that isn't a simple extension of first-year calculus. Okay? And often in a context of what you know about physics and what you will know.